We're going to start with a review question from Friday's lecture. We have a sample of oxygen at half an atmosphere, and it occupies a volume of 10 liters at 0 Celsius. What is the pressure of the gas if we move it up to 15 liters and 25 Celsius? So while you're working on that, I am going to pass back your quizzes from last week, and then we'll come back and talk about it in a few minutes. All right, so let's go ahead and see how we did. So in this chapter, there are basically two gas laws that we have to know really, really well. The first is the ideal gas law. We talked about it at the end of Friday's lecture. PV is equal to nRT, Pivner. That's the one that we're going to use for anytime we're describing a single gas and trying to figure out everything we can about that single gas. That's also the one that we'll use in any kind of chemical reaction situation. The other one is the combined gas law, the one that we actually talked about first. P1V1 over T1 is equal to P2V2 over T2. And this one we're going to use when we see that a gas has changed conditions. It's changed its temperature, it's changed its pressure, it's changed its volume. Now, the thing that we have to remember about this equation is that those temperatures have to be in Kelvin. So we've got to add 273 to each of these. So 0 Celsius becomes 273 Kelvin. 25 plus 273 is 298 Kelvin. So if you skip that step, you got a really funky answer here because you end up having to divide by 0. And any good mathematician would tell you that's not generally something we recommend. So our starting conditions, we have half an atmosphere, we have 10 liters, and we have 273 Kelvin. And on the other side, we have an unknown pressure, 15 liters, and 298 Kelvin. To get P2 by itself, I'm going to have to multiply both sides by 298 Kelvin and 15.0 liters. Everything cancels on the right-hand side other than P2. My Kelvin cancel, my liters cancel, giving me just atmospheres for the pressure. Now I just need to multiply all the numbers together. 298 multiplied by 0.5, multiplied by 10, divided by 15, divided by 273, to 3 significant figures, 0.364 atmospheres. With these kinds of problems, it's always important that we ask ourselves the question, does this make sense? If you recall, one thing that I made mention of specifically on Friday is that if we have pressure changes or volume changes coupled with temperature changes, the PV changes are always going to be more significant. So we're talking about the expansion of the container, which is going to drop pressure, versus the heating up of the gas, which would cause the pressure to increase. The expansion is going to be much more significant. That's why we saw the drop in pressure. Any questions with this before we move on to some more ideal gas law calculations? All right, taking that silence for no. Let's talk about another application of the ideal gas law. In this situation, we can talk about using the ideal gas law and standard temperature and pressure to figure out the density of a gas. The problem with these kinds of calculations, honestly told, I don't use them particularly much. It's very useful if you have that equation in hand at the moment. But if you have a simple understanding of the ideal gas law, we can manipulate it appropriately. Why this is important is buoyancy. By knowing the density of a gas, we can figure out where that gas is going to exist in our atmosphere. Lighter gases are going to exist higher in the atmosphere. More dense gases are going to exist lower in the atmosphere. That's why there's so much carbon dioxide and oxygen down here, because of the gases, they're considerably heavier than, say, your hydrogens and your heliums. Now, when it comes to something like a hot air balloon, well, that's actually something else at play. That's an application of Charles' law. When we heat up the air in a hot air balloon, we're not changing any of the gas, but we are expanding its volume. So the amount of gas doesn't change, but the volume does. So that means that the density is going to go down as a result. And we heat it. The more we heat it, the more it expands. The less dense it's going to be, the more that balloon can go up. So what we're looking at here then is this. Here's an example of a gas density problem. Now, with that equation that we just had, E is equal to the molar mass times the pressure over RT. If you know that equation, problems like this are pretty straightforward, because all that we need to do is just simply input the correct variables in the right places. And really the only thing that's stopping us here is we have a pressure in millibar, but we don't have an R value in millibar, so we would have to do that conversion. The conversion itself, not too terribly difficult. We just need a table of conversion values. With 1 atmosphere being equal to 13.25 millibar, we could easily turn that into atmospheres and go about our business as we were before. So 1,024 millibars with 1,013.25 millibar in 1 atmosphere. For significant figures, it's 1.011 atmospheres. So putting in the values, 28.8 grams per mole, multiplied by 1.011 atmospheres, divided by 0.08206 liter atmospheres per mole Kelvin, and 26 Celsius would be 299 Kelvin. So if I follow through here, atmospheres cancel, Kelvin cancel, 1 over moles cancel. All that is left is grams in the numerator and liters in the denominator. 28.8 times 1.011 divided by 0.08206 divided by 299 would give us three significant figures, 1.19 grams per liter. So like I said, if you have this equation, that's a very easy way to figure out gas density. If you don't, you can still go back to the ideal gas law. All that you need to do is manipulate the equation. And what I mean by that is, if this is our equation, PV is equal to nRT, what we can find is something like the molar density, where I can turn this into N over V is equal to P over RT. This would give me moles per liter. In a solution, we would call that molarity. Here, we're just going to call it moles per liter. All I have to do once I find that is multiply it by the molar mass, and it would turn the moles per liter into grams per liter. So if I follow that same process, I still have the same pressure, 1.011 atmospheres. The R value is still the same, 0.08206 liter atmospheres per mole Kelvin. Temperature still 299 Kelvin. And if I do my crossing out, the atmospheres cancel, the Kelvin cancel. What I have at the end of this process is 0.0412 over liters per mole, which, if you remember from algebra, a reciprocal of a fraction just flips that fraction in the denominator. So 0.0412 moles per liter. And now if I multiply that by the molar mass, 28.8 grams per mole. The moles cancel, 0.04 times 28.8. I'm going to get to the same three significant figures, 1.19 grams per liter. So why go through all this to show you this? Again, it comes down to your equation sheet doesn't have every single equation on it. So if you've memorized this density calculation with this formula, great, use it. It is simpler. But if you didn't, understand that this has its roots in the ideal gas law. And if you can use the ideal gas law to get a similar ratio, all that you have to do is convert that ratio of moles per liter into grams per liter by multiplying by the molar mass. That's all that I'm trying to show you here. The ideal gas law is versatile. You're going to find it useful anytime you have to do calculations involving moles. And speaking of which, we come to the part that you've all been dreading. How do I interpret and how do I include the ideal gas law into stoichiometry? Because I love stoichiometry so much, how could I possibly not want to use it every way I can? Well, the good news out of this is that it's pretty simple. The ideal gas law gives us the link between what we can measure about a gas, its volume, its temperature, its pressure, and what we don't know always about a gas unless we weigh it and we know its identity, the number of moles. So with a rearrangement of the ideal gas law, we can convert between those parameters that we can measure, pressure, volume, temperature, and moles, which we have a harder time measuring. Or, if we're flipping it around, and we're trying to figure out how much gas we're going to produce, or how much is supposed to be produced, like a theoretical yield, we can flip this around again and use that number of moles and that temperature and that pressure to determine the volume that is expected. And so if we come back to this image, throughout some of the chapters, chapter 8, we added some boxes related to molarity and solution concentration. We can add some boxes here as well. If we know the volume of A in the gas phase, we can relate it to moles using the ideal gas law. Same thing with volume of B over here on the other side. So this just becomes a part of the scheme that we've kind of built up since we first introduced this all in chapter 7 a couple of months ago. And even goes back to chapter 2 because we used a similar schematic to talk about the relationship between elements and compounds and individual components of a compound when we first introduced the idea of the mole in general. So let's take a look at a couple of example problems to help illustrate this point further. Okay, we are told that automobile airbags will inflate during a crash or a sudden stop through the rapid generation of nitrogen gas through the massive decomposition of sodium azide. Reaction is there on the board. 2 sodium azides decomposing into solid sodium and gaseous nitrogen. The question is this: how many grams of sodium azide are necessary to produce enough nitrogen to fill a 48 by 48 by 25 bag to a pressure of 1.2 atmospheres at 15 Celsius? Now, there's a lot of information that is going on in here. But what we want to come back to is, again, this idea that we are starting with some preset amount of nitrogen. And once we figure out what that amount of nitrogen is, then the rest of the steps are just stoichiometry. Conversion from nitrogen gas to sodium azide to grams of sodium azide. We just got to figure out how much nitrogen we're talking about. And we've been given some information. We've been given a pressure. We've been given a volume. We just have to calculate it. And we've been given a temperature. So we've got everything we need to use the ideal gas law. We just have to make sure that we dress it up a little. 15 degrees Celsius, 15 plus 273, that's 288 Kelvin. We've got some sort of rectangular prismatic airbag here, 48 by 48 by 25. So let's multiply those dimensions together. 48 times 48 times 25. My calculator gives me 57,600. Unit there would be centimeters times centimeters times centimeters. So this would be centimeters cubed. Now the important thing to know in this one, how do I turn centimeters cubed into liters? It's not actually as difficult as you think. What? They're not equivalent, but cubic centimeters is equivalent to a volume unit that you do know. Goes back all the way to chapter 1. Definition of a milliliter as a cubic centimeter. So that 57,600 cubic centimeters, that means that it's 57,600 milliliters. Divide that by 1,000, it's 57.6 liters. So now we have all three of the dimensions in the units that we want it to be. We're going to turn the ideal gas law into a method to conduct and create moles. Pressure was 1.20 atmospheres. Volume is 57.6 liters. Value of R, still 0.08206 liter atmospheres over moles times Kelvin. 288 Kelvin is my temperature. So Kelvin cancel out, liters cancel out, atmospheres cancel out. All that is left is the reciprocal of 1 over moles. So moles will be the unit. 1.20 times 57.6 divided by 0.08206 divided by 288. To three significant figures, we would get 2.92 moles of nitrogen. So if we go backwards to our mole map here, we've just converted volume of gas into moles. Now we're going for grams of the other substance, so we just got to follow the rest of the map. We need a mole to mole conversion using the balanced chemical equation. We need a mole to gram conversion using the molar mass of sodium azide. So using the balanced chemical equation, 3 moles of nitrogen for every 2 moles of sodium azide. And then the molar mass of sodium azide, 1 mole of sodium azide. Sodium 22.99 plus nitrogen 14.01 times the 3 of them, 65.02. Moles of nitrogen cancel out. Moles of sodium azide cancel out. The 3 significant figures. (127 grams of sodium azide. Any questions with this application of the ideal gas law for a chemical reaction? All right, so we just have a couple of other concepts that we want to look at to kind of close out the chapter here. You've actually applied a couple of these already. So what do we do if we have a mixture of gases? Well, if we have a mixture of gases, we understand that because the gases are going to be so far apart from each other, we know that they're going to act independently of one another. It's not going to be any intermolecular forces to consider or any kind of cooperative kinds of work. So we can consider that each gas has its own individual pressure. We call that individual pressure a partial pressure because it is part of the overall pressure that we would see by the gas. So if we're measuring the pressure of this room, we're going to be measuring the total pressure exerted by all of the different kinds of gas that are in this room in total. And so we would measure the total pressure, but if we were able to isolate the carbon dioxide, isolate the oxygen, isolate the nitrogen, isolate all the trace amounts as well, what we would find is that their individual pressures would add up to the overall pressure that we measure. This is something known as Dalton's law of partial pressures. And Dalton's law of partial pressures has some really interesting applications to it, because it allows us to make some adjustments along the way if we run into situations that are kind of unique and different. So for example, what if I wanted to know what the individual pressure of carbon dioxide was in this room? Well, if I was able to determine the concentration of carbon dioxide in this room using mole fraction, I could do just that. And the equation for doing that would look like this. Now, if that looks familiar to you, it's because basically Raoult's law is the same thing, only with solutions. And if you get into higher levels of chemistry, it gets actually really interesting, because what we will find is that the laws governing what's in the solution are going to be different what's in the gas mixture above it. You can have one combination of liquids in solution at very different concentrations than the vapors, based upon the vapor pressure of the substances themselves. And it makes for some really interesting kinds of properties that you start to look at. But again, the idea here, the guts of this, is pretty much the same. This is very similar to Raoult's law. Calculation, mole fraction of the piece that we're studying multiplied by the total pressure will give you the partial pressure. And of course, you could work this backwards as well. If you knew the partial pressure and the total pressure, you could figure out the mole fraction of the substance that you were interested in. Where we use this the most often, though, and you did this in your lab, that molar volume of gas lab that you did, basically use this principle. You were collecting oxygen gas over water, and because you were collecting it over water and water evaporates, that volume of gas that you measured and the pressure that you assumed to be atmospheric was actually a combination of two gases. It was the oxygen gas that you were interested in and a little bit of water vapor as well. And so we had to take out that water vapor in order to do the calculations with the oxygen. We couldn't just leave it alone. We had to take out the water vapor so that when we were doing the ideal gas law or the combined gas law, we were accounting for, okay, this is just the oxygen. It's not oxygen plus everything else. And as a result of that calculation and that correction, should have got pretty good percent errors in that experiment. So let's take a look at this last application, and then we'll call it a day. During the decomposition of potassium chlorate, 92 milliliters of gas is collected by the displacement of water at 25 degrees Celsius. If atmospheric pressure is 756 millimeters of mercury, what mass of oxygen was collected? Now, the piece of information that we are missing here is we know that the atmospheric pressure is going to be equal to the pressure of the oxygen that we're interested in, plus the pressure of the water vapor, which we are not interested in. What we need is the vapor pressure of water at 25 Celsius. And that is 23.8 millimeters of mercury. So with that in mind, now we can say 756 millimeters of mercury is equal to the pressure of oxygen plus 23.8 millimeters of mercury. So if I subtract 23.8 from both sides, 756 minus 23.8 would give me 732 millimeters of mercury. We're going for the mass of oxygen, so we need to figure out the number of moles. N is equal to PV over RT. Pressure, 732 millimeters. Volume, 92 milliliters, turned to liters would be 0.0920. Since we're in millimeters of mercury, 62.36 liter millimeters per mole Kelvin. 25 Celsius is 298 Kelvin. So multiply it all together, 732 times 0.092, divide by 62.36, divide by 298. I get 3.62 times 10 to the negative third moles of oxygen. I need to turn the moles into grams. 1 mole is 32 grams. So I'm not going to get much. 0.0116 grams of oxygen would be the product if this is what I made. But understand, you can take this a lot of directions. From here, with moles, we went to grams. We could have easily gone to moles of potassium chlorate. We could have easily gone to grams of potassium chlorate, formula units of potassium chlorate. We could have gone a lot of different ways. But the main thing I wanted to get across today was ideal gas law is very versatile. There are a lot of different calculations that you can do with it.